Okay, hello everyone. Welcome to Stat 310 Lecture 11. So today we're going to continue, and we're getting close to the end of the discussion on Chapter 8, which is this estimation chapter. And in particular, we're going over one of the most important and one of the more widely used estimation procedures, which is maximum likelihood. So today we're going to finish that discussion in terms of how to calculate the maximum likelihood estimator. So we talked about that in lecture 10. And so today we're going to finish with another example of that and then just kind of go over the procedure again. And then I'm going to get into the question of, of also interest is, we want to talk about the distribution of that maximum likelihood estimator so we can go and do other things like calculate confidence intervals, because so far we've only really learned about how to calculate that maximum likelihood estimate, but we'd like to say more about, can we find confidence intervals and what can we do in terms of inference based on that. And so that'll be the main focus of the lecture today. So I just want to remind everyone, so we introduced this in the previous lecture, but it's worth going over again because it's such an important procedure, and we're going to see this a lot for the remainder of the course. So maximum likelihood estimation. So the general idea is that you have n independent random variables drawn from some PDF or PMF. So here, F here could be a PDF or a PMF. So, okay, so it could be like the PMF for a Poisson distribution or the PDF for an exponential or a normal distribution, but it's some underlying distribution. And then there's some unknown parameter theta of interest. And so the maximum likelihood procedure is a general procedure where you just take this notation argmax means just the theta value that maximizes this product of the function. So this is like the likelihood function, and so you're taking the theta that maximizes it. And a useful thing to do that we saw in numerous examples in the previous lecture is to take logs, because the log of the product is the sum of the logs. So the argmax isn't going to change once you take logs. And we're going to see today the sum of the logs is actually a very useful thing to think about when we're talking about maximum likelihood estimation. And so we're going to do another example today and just kind of review this general procedure. And then we're going to move on to talking about the distribution for theta hat ml, and the log of f is going to come in there as well. So that's why I'm introducing it here again. So let's go through another example just to remind ourselves of exactly how the whole procedure or calculation works. So here we've got an example where x1 through to xn is independent with PDF here. I've used this notation. Xi has this PDF, it's PDF f, and the way the PDF is defined is theta x to the power of theta minus 1. So theta is the underlying parameter of interest, and we're asserting that it has to be greater than or equal to 1. And then we're also saying that x has to be between 0 and 1. Okay, so this you can show that this is a valid PDF if you integrate and take to 1. This is a valid PDF for all your choices of theta. And so we want to find theta hat ml. Okay, so remember that the procedure asserts that okay, and once again, it's going to be useful to take logs because the PDF is going to be look a little bit easier to deal with, and we, rather than taking products, we can take sums when we deal with logs, because the log of the product is the sum of the logs. So now let's work out what this log is. So if we take log of, so let's just go over here. So log of theta x to the theta minus 1 is just log of theta plus theta minus 1 log of x. Okay, and so we can rewrite this out as Okay, and so when we take out the sum, we end up with this, or when we move the sum through, we're going to have that this is n times log of theta, because you're summing up log theta n times, and then plus theta minus 1. Okay, and so how do we take the maximum? So as we saw in the previous lecture, the most natural way to do that is to differentiate. So if we differentiate, so then we have so differentiate and set to 0. So if we do that, if you take the derivative, so let's call this, say, this is like our likelihood function, which I'll call L of theta here. If you take dl of theta hat ml d theta equals 0, so that's just saying if you take the derivative of that and set it to 0, and when you plug in theta hat ml, what we end up with is if you take the derivative of the log, it's just n over theta. So remember, this is the natural log that we're talking about here, and then the derivative of the theta is just whatever that term is. So we treat everything that doesn't involve theta as a constant, and we get this as the overall derivative, and so therefore we have And so another way to think about it, or if we do some rearrangement, we get that theta hat ml equals the negative log of the sum of the xi's over n. So theta hat ml is another way to write it out is just log of 1 over xi divided by n. And the thing to note here is the xi's are all between 0 and 1. So when you take log of 1 over that, that's always going to be a positive number. So this, this theta hat ml that we get will end up being something positive. So one thing to note here is that theta hat ml will be very different from theta hat mm, the method of moments estimator that we covered in the last couple of lectures. Okay. And some of you might be thinking that, well, we've taken the derivative and shown that it's 0, but how do we kind of show that that's a maximizer? So the way you do that, and this is also going to be important later, but you don't have to do this for every question, but just to know how you would do it. So theta hat ml is maximizer because it could be, if you recall calculus, if the derivative is 0, that could be a maximum, it could be a minimum, or it could be some kind of saddle point or something. So what we would need to show is that the derivative of L of theta hat ml d theta, when you take the double derivative, for that to be a maximizer, it means that this double derivative has to be less than 0. So can we show that that's actually true? So if we look at this derivative and then take another derivative, if we look at d squared L of theta d theta squared, so you know that the first derivative is n over theta plus this sum of the logs. So the double derivative is just negative n over theta squared, and that's clearly going to be less than 0 for any theta bigger than 0. So you can see that where this is certainly a minimizer or maximizer. So therefore theta hat ml is maximizer of log likelihood or likelihood. Okay, so yes, as I mentioned, this we saw many examples where the maximum likelihood estimator was very similar to the method of moments, or the same, in fact. But in this case, they're very different because this is really like kind of an average of logs rather than the overall average. And so I think it's a useful exercise. Find theta hat mm in this case. And so this is a good exercise for you to to see that kind of how the method of moments procedure works. So so back onto maximum likelihood estimation, which is the focus of what we're talking about right now. In general, finding theta hat ml involves maximization. And so this is typically differentiation and setting to 0 as the there was that one example involving the uniform from the previous lecture where the maximizer was actually at one of the endpoints, which meant that you weren't differentiating and setting to 0, but you were just picking one of the endpoints. But in most cases, you'll find that differentiation and setting to 0 it gives you the maximizer. So I'll just say or lies at endpoint of function. Okay. So now we ask kind of the other really relevant question that we think about when we think about estimation is that, so, just when you give someone an estimate, typically they say, okay, that's great, but how confident are you that that estimate is, a good estimate? Like, is it accurate? And so that's where you really need to ask the next important question, which is, what is the distribution of that theta hat ml, or can we find an approximate or an exact distribution for that? And from that, can we deduce some confidence intervals? And that's really what we're going to be talking about starting from now. So just to kind of, go back to the general framework, because, we like to sort of keep track of things through this framework. So this is in 8.5 we're talking about specifically, which is maximum likelihood estimation. So we have sample data, x1 through to xn. Then we have the the distribution and parameters. So, like everything we see in chapter 8, we try to be as general as we can. So xi has some distribution, f of x theta, and we assume that they're independent. And theta is the parameter of interest. Then the other question is the estimator or the statistics. So these are functions of the data, and so we've seen that what we've talked about so far is the maximum likelihood estimation. Estimate, which satisfied Okay. And so now, and so we've kind of covered the first three components of this framework, and so now we ask the question, which is the fourth and fifth kind of components of the framework, which is okay. So we're gonna mainly focus for the rest of this lecture and also possibly part of the next lecture on the question of what can we actually say about theta hat ML from an inference point of view. So firstly, can we determine what the distribution of theta hat ML is, and how it involves the true parameter theta. And the other question is, what can we say about theta hat ML being close to theta? So, can we use some approximate or exact distribution that we calculated from the fourth component to say something about to come up with confidence intervals or some other kind of inference for the distribution theta. Okay, so we're gonna ask the question of it's basically it's generally impossible to find the exact distribution of theta hat ML. I mean, it's a pretty general procedure. In some special cases, like for example, if our data is normal, we can come up with kind of exact distributions. We've already kind of seen in this course that when your data is not normal, it's generally quite difficult to come up with exact distributions, and that's indeed the case here. So we're going to ask the question, what is asymptotic distribution of theta hat ML? Okay. So to get to we're going to build up to that slowly. Or we're going to get to that in the next 20 minutes or so. But we're going to need an important definition first, because it's going to relate to kind of the asymptotic variance of the maximum likelihood estimate. So we're going to introduce this definition, which is the Fisher information. So I'm going to state the definition first, and then we're going to kind of unpack it and do some examples. Okay, so what does this mean? So I have theta here. So let's try to unpack this a little bit. So note that I of theta is just a function of theta. And so what are we doing here? We're saying that So what we're doing is we're noting that f of xi theta is a random variable since xi is a random variable. So this is something you're potentially not overly used to seeing in this class, is that xi is a random variable, and all that f is a function. So remember that f of x theta is just a function indexed by theta. So the example we just saw is like f of x theta is like theta x to the theta minus 1 for example. So remember that functions of random variables are still random variables. And so therefore we can also say that log of f of xi theta is a random variable. And therefore we can also say that negative d squared log of f of x I theta d theta squared is also a random variable. So the only thing that's a little bit kind of potentially tricky to get your head around is that xi has this distribution f of x theta, and we're actually kind of taking that function, we're taking the log of that function and then its derivative, and then taking an expectation. So because it's a random variable, we can take expectation of so because it's a random variable, we can certainly take the expectation of any random variable. We're going to see what that looks like shortly. Okay, so we're going to build up, the whole point of doing this is we're going to build up to the asymptotic distribution of the theta hat ml shortly, but I just wanted to first kind of cover this concept well so that we know kind of what it is when we get to it. So let's do some examples. So one thing so let's do some examples here. So let's go back to the Poisson example. So here you have x1 through to xn is distributed with Poisson distribution with parameter lambda. So here your theta is just lambda, and your xi here is f of x theta. This is a PMF in this case. So f of x theta equals e to the negative lambda to the x over x factorial. So this is also relating to likelihood, because remember we sort of took logs of this PDF to work out the sum of the log likelihood. And so once again, we can take logs of this as well. So log of f of x theta is just negative lambda plus x log lambda, or minus log of x factorial. Okay. And so now let's so we can certainly plug this in now as a random variable. So we have that log of f of xi theta equals negative lambda plus xi log of lambda minus log of xi factorial. and we can take derivatives. So let's take derivatives. So we need to take the derivative twice. So if we do it once, so that's going to be, if we just take this derivative, it's -1 plus xi over lambda. And then if you take the derivative again, that is going to be the -1 disappears and we just get negative xi over lambda squared. Okay, so now let's take the expectation of negative d squared. Sorry, I've used theta and lambda interchangeably here. So theta here is just lambda, so just... Okay, and so all that is just taking the expectation of xi over lambda squared, right? And so that's 1 over lambda squared times the expectation of xi. And so remember that this is a Poisson random variable with parameter lambda, so this is just 1 over lambda squared times lambda, and so this is just 1 over lambda, okay? So therefore we have that I of theta, which is just I of lambda, is just 1 over lambda. And note that this is bigger than 0, and in general we'll find that, so I of theta, sorry, this should be I of lambda, sorry. I of theta always greater than 0. So if you do your calculation and you get something negative, you know you've done something wrong with the information, and we'll see that later because this is going to be related to the variance for the maximum likelihood estimate. So let's do another example. We're going to do a few examples just to get ourselves used to this idea of Fisher information. One of the key components to working with the maximum likelihood estimate is to be able to calculate the Fisher information. So that's why I'm going through a few examples here, and this is going to allow us to define confidence intervals. So So here we're assuming things are Bernoulli P, so theta here is equal to P, which is a probability of flipping a 1. And note that here your f of xi theta, or P, has this kind of interesting form, which is it's just P for xi equal to 1 and 1 minus P for xi equal to 0. So now what I'm going to do is I'm going to show you a very useful trick. It's also in the textbook, but something that's very useful for the Bernoulli distribution, just so you can write it out as a function and not just see it as kind of these two numbers that's an indicator. So what you can actually, another way to write this, and you can check this yourself, is that this is just P to the power of xi times 1 minus P to the power of 1 minus xi. And the reason for that is because if you plug in xi equals 0, you're just going to get 1 minus P, because the P to the 0 just becomes a 1. And the other thing is that if you plug in xi equals 1, the 1 minus P disappears because you're just getting at 1 minus P to the 0, and the P will just be to the power of 1. So you can see that this actually gives you the right distribution, and this is going to be really useful when we start to talk about, when we want to start taking logs and calculating Fisher information and so on. Okay, so this is something to just, a useful way to express the PMF for the Bernoulli. So once again, we have xi is in 0 or 1, but we're just kind of writing it out in this way. So now let's, find I of theta, which is I of P. So the first thing we do is take logs. So we get that this is xi log p plus 1 minus xi log of 1 minus p. Okay, and now we can start taking derivatives. So d log dp is just going to be, we're going to get xi over p and then minus 1 minus xi over 1 minus p. I believe that's right, or should it be a plus? I think that's correct. Yeah, that's correct. And so then we also, when we take the double derivative, you're going to get negative xi over p squared, and then minus 1 minus xi over 1 minus p squared, because we have negative to the negative in here, which becomes a positive, but then we raise to the negative one, so it goes back to being a negative. Okay, so now let's look at the expectation of negative d squared log of f of xi p dp squared. And so that just becomes the negative, the negative becomes a positive, so all of these negatives go away, and you just get e of xi over p squared, and then plus e of 1 minus xi over 1 minus p squared. And the expectation of, so note that because xi is Bernoulli p, we have the expectation of xi equals p, right? Because, it's just the expectation is just the probability that you get a 1. And so you end up with that I of p is just p over p squared plus 1 minus p over 1 minus p squared. And so you end up with 1 over p plus 1 over 1 minus p. And when you put that together, you should just get that this is just exactly 1 over p times 1 minus p. Okay, so this is I of p. And note that here p is between 0 and 1. And also note that clearly that we have that I of p is bigger than 0 here. So that's another check to see that we've done things correctly. Okay, so this is the Fisher information for the Bernoulli distribution. We're going to see how this is useful shortly. Okay, and we're going to do one more example just so we're really kind of comfortable with this concept of how to calculate Fisher information. So this goes back to the example we did at the beginning of class. So we have that we have independent drawers from this distribution that we saw at the beginning of class, which is where theta is bigger than or equal to 1 and x is between 0 and 1 is the PDF. So this is a PDF here. So we want to find I of theta here. So log of f of xi theta is log of so we already calculated this, but we're going to do it again. Just so that we sort of know what's going on. And then if we look at the derivative, so we just get that this is 1 over theta plus log of xi. So we did this calculation already because to calculate the maximum likelihood estimate, we took the derivative of the log. And then if we take the double derivative, then we just get negative 1 over theta squared because there's no term involving theta in the second term. So therefore, if we look at then you're just going to get 1 over theta squared. Okay, and as we saw earlier, this is bigger than 0 since theta is bigger than 0. Okay, so this kind of, again, so we have that the Fisher information is equal to 1 over theta squared. Okay, so we've seen 3 examples of how to calculate the Fisher information. The thing that's nice in the third is that all the xi's disappear, so we don't have to take an expectation. It's just a constant. We saw that in the first 2 examples for the Bernoulli and the Poisson that we had to take this expectation. And so this was just an exercise in calculating Fisher information, which involves just essentially derivatives and expectations. But the more relevant question is, why is this concept useful? And so it turns out that I of theta is asymptotic, or I should put usually, because there are some conditions which we won't go too far into, is usually the asymptotic variance of theta hat ml. Okay, and so essentially this leads to the following result. It's result or theorem. So root square root of n, and you see this Fisher information come in. So this is, you can think of it as like it's a central limit theorem type of result, but we've got this kind of asymptotic mean and variance. And another way to write that so another way to write that as an approximation is that theta hat ml approximately has a normal distribution with a mean of theta, so that's the true underlying parameter, and a variance of 1 over n times I of theta. Okay, so you have this n coming in because, as you get more data, you kind of expect to be more accurate. And then you have this Fisher information coming in there as well. Okay, so I should say 1 over I of theta is usually the asymptotic distribution variance of theta at ml. If we get time, I'm just gonna just provide a pointer to how to find the proof of this, because the proof's quite technical, and I potentially just want to give some insight to it, but I'd rather for now just go through some examples of this. So we'll go back to this Poisson example that we've seen today and in the previous lecture. So So if we want to find lambda hat ml and its asymptotic distribution, so we hopefully recall that lambda hat ml is just the sample mean, so x bar, which is okay. And then we also so the only ingredients we really need are the is firstly the x bar and then the Fisher information. Those are like we need to find kind of theta hat ml and the Fisher information, and that really tells us everything we need to know. So I should say that this is needs some regularity conditions, but I'm not going to sort of go into the details of that. They're quite technical. In general, if you're asked to find an asymptotic distribution for maximum likelihood, the way you're going to do it is what I described, where you find the Fisher information. So in the examples that you'll see, and in most examples that you generally see, these conditions that I talk about, these conditions that I mentioned but sort of don't go into, will be satisfied. So then recall that I of lambda here, the Fisher information was 1 over lambda. And so the other thing to note is recall that, variance of xi here is lambda. So, what we potentially learned from before was that if you have, so what that kind of says is that square root of n times 1 over lambda, and then you can say like x bar minus lambda converges to normal 0, 1. And we actually kind of knew this already from what we've already studied. So another way to look at that is that square root of n x bar minus lambda over lambda is just normal 0, 1. In fact, this should be a square root of lambda. Okay, and so, this is just saying that square root of n x bar minus e of xi, which is lambda, over square root of variance of xi is just normal 0, 1. So in this particular case, because we have this special case where the maximal likelihood is the sample mean, we already know the asymptotic distribution of the sample mean by the CLT. So the maximum likelihood result doesn't give us anything new, but I just wanted to show it to you so it confirms what we already know from the CLT. So this is consistent result from the CLT. So let's do another example, which we kind of already know the answer to and we've seen before. So x1 through to xn is Bernoulli P, independent. And we want to find P hat ml and asymptotic distribution. Of P hat ml. Okay, so I'm not sure if we did this calculation or not, so we're going to go through it again, but P hat ml is argmax of P of this likelihood function, and once again we can take logs. Okay, and so once again here we're going to use this useful result that f of x p here is just p to the x times 1 minus p to the 1 minus x. So therefore log of f of x p here is x log p plus 1 minus p log of 1 minus x log of 1 minus p. And so therefore we have okay, and it's convenient to write this out with all of the, where we're going to put all of the xi's together. So you get xi as log of p over 1 minus p. I'm just using properties of logs here. And then plus log of 1 minus p. Okay, and so let's take derivatives to set to 0. So we want to take a derivative of this whole function. We'll call that L of p as a function of p. So we're going to get that this is just as I go through this calculation. So this whole thing should that be negative or positive? That should be a yeah, I think that should be that's correct. So this thing should be equal to 0. And then when you multiply through, you should just get that if you multiply through by p times 1 minus p, you're just going to get 1 minus p times summation I equals 1 to n xi. Okay, so if you multiply through like that, this is what we're going to get. N times p should be equal to, when you rearrange, you'll just get that this is the case, and so p hat ml equals the summation I equals 1 to n xi over n, which is just equal to x bar. Okay, so once again we have, therefore we have p hat ml equals x bar, which is just the sample mean. Okay, and so therefore, and then we also calculated the Fisher information earlier. So I of p is 1 over p times 1 minus p. So therefore, the overall asymptotic distribution of p hat ml is square root of n times I of p hat ml minus p should go to normal 0, 1. So we can plug all of that in and we'll get that square root of n over p times 1 minus p. And then we'll get x bar minus p converges to normal 0, 1. And once again, you'll note here that this is nothing new. This is just the CLT again, that you can show that this is just So again, this is not actually anything new that we don't actually know. This is just confirming that the result has some kind of merit because it shows us things that we already know. So this is same as result for CLT. So I mean, a couple of you might be thinking like, what's the point of this? We've got this new result for maximum likelihood estimation, but we've just applied it in cases that it's just given us the CLT back. So why is this kind of useful or interesting? And where it's going to be useful is if where we're going to find something new is in cases where the maximum likelihood estimate is not the sample mean. And we've already seen an example of that. So let's finish with one more example where we're going to get something that's kind of new and different from what we've already seen. So here, this goes back to the first example we saw in class today. So we have that this is independent draws from this distribution. So here we have x between 0 and 1, theta bigger than 1, and f of x theta. So we found that we want to find so sorry, I'm just let me just get out of this. So we want to find theta hat ml and its asymptotic distribution like we've done before. So we know that the asymptotic distribution satisfies so this is just putting together calculations we've already done. So recall that theta hat ml is just the sum of the logs, or we write it in this different way as the log of 1 over the sum of the log of 1 over the x's. So this is kind of this is an average of logs rather than the overall average. So certainly this is not going to be the sample mean, and so we're going to get a very different result to what we get for the central limit theorem. And then we also calculated that I of theta is just 1 over theta squared, right? So therefore we can say is that therefore we have that root n times theta, theta hat ml minus theta goes to normal 0, or this is 1 over theta, sorry. Okay, and so therefore we can kind of say that another way to put it is that so this should be 1 over theta squared, I'm sorry. Okay, so and the thing I'll sort of note here is that does not follow from the CLT in this case. It follows from something maybe similar, but it's not exactly that, because the in this case the theta hat ml is, and I'll just say that since theta hat ml is not equal to x bar in this case, so when you don't have theta hat ml equals x bar, you can't really kind of use the CLT very much. And the idea behind that is that idea is that theta squared is equal to actually the variance of log of 1 over xi, rather than the variance of xi. So you can think about it as like this is essentially kind of why this is essentially where that theta comes from. So the next kind of question is like, how do we use this asymptotic result to find confidence intervals or do inference? So we know that is normal 0, 1 when you have this Fisher information term, and so the normal approximation, like kind of when you sort of put that in, is this that theta hat ml is going to be approximately normal with mean of theta and then a variance of 1 over n times I of theta. But I of theta depends on theta, and this was an issue that we encountered when we were doing the Bernoulli example and the Poisson example as well. So I of theta depends on theta, right? And so this is a challenge because you don't actually know what that asymptotic variances is. So use plugin. I of theta is approximately I of theta hat ml. And so you can say that theta hat ml is approximately normal with mean of theta and a variance of y of theta 1 over n of I of theta hat ml. Okay, and the final thing I'll say today is so to find, these 1 minus alpha times 100%, so that could be 95%, it could be, any other percentage. We now have a procedure that allows us to do that using the maximum likelihood procedure. So it's going to be like theta is going to be in theta hat ml and then minus z alpha over 2. So this is the z score. And then this is going to be times 1 over n times I of theta hat ml. And then because we know that things are normally distributed, I of theta hat ml. Okay. And we're going to see examples of that in the next lecture. So here's z of alpha over 2, just basically equals to so this is just going to be the z score that that gives a tail of size alpha over 2. Okay, and so this is for the standard normal. Okay, and so we're gonna actually do this with a few examples in the next lecture, but that's gonna be it for today. And so there was a lot to take in today. So I think just through the homework and through these examples, just try to get yourself comfortable with doing calculations of like the Fisher information and the maximum likelihood estimation. We're gonna do a couple more examples like that in the next lecture. All right, thanks very much. That's it for today.